Good evening, everyone. Welcome to the NYIT School of Architecture and Design lecture series. Tonight we have Fabio Gramazio, who's going to give us a talk on his work. We were just having a small conversation here about, I had seen them lecture back in around 2008 at the Storefront for Art and Architecture about the winery project. And so I'm looking forward to seeing the work that they've done since that time. I was taken and understood this kind of dynamic process that they were looking to try to achieve with this robotic building of these interesting brick walls and the texture and the process that was made to develop these. So I think we'll have a kind of interesting understanding about architecture and building process and how we can use technology to develop both of those things further. So I will, my name's Robert Cody. I'm the Associate Dean of Architecture here at the School of Architecture and Design. Maria Perbolini, our Dean, couldn't make it here today. She's in Florida right now doing a little bit of fundraising activities with some of our alumni. So I think she has a good opportunity there, so it's great for her and for us. So I will now hand it off to Naomi Frangos, who will give the introduction to the lecture and talk a little bit more about the lecture series. So thank you all for coming.
Thank you, Rob. Good evening, everyone. I'm Associate Professor Naomi Frangos, co-coordinator of lectures and exhibitions. And on behalf of Dean Perbolini, the faculty of New York Institute of Technology, School of Architecture and Design, I just want to thank you all for coming here tonight. Tonight, we're very honored to host Fabio Gramazio, partner from Gramazio Kohler from the ETH in Zurich, Switzerland, speaking about the Robotic Touch, How Robots Change Architecture, an incredible body of research relevant to the focus of our 2016 spring lecture series, Scalable Digital Processes. This spring, we heard from Pablo Lorenzo Eiroa on architecture information, the post-digital as design authorship, and Carlo Ratti on sensible cities. And on April 20th, we will host a symposium on stereotomy digital construction tools led by Giuseppe Falacara, NYIT Associate Visiting Professor and Professor at Polytechnic of Bari, accompanied by Christian Pongratz, Interim Dean, New York Institute of Technology, School of Interdisciplinary Studies and Education, Shajay Bhushan from Zaha Hadid Code, Eduardo Tibuzzi from PR Act 2, Maurizio Barberio and Michaela Corella from New Fundamentals Research Group, Dustin White, our own Director of Digital Technologies and Fabrication, Bruno Camberneau, Director of Institute for Research and Training in Stone Professionals for the Compagnon du Devoir, and there will be an exhibition at Par Excellence in Manhattan of the work produced, which will also make its way to our gallery in Old Westbury. So this series brings together various current leading voices in digital processes as a way to extend and integrate the discussion at NYIT within the broader contexts of pedagogy, research, and practice. Today's common placement of digital technologies can be found in its attempt to categorize its use in terms of a particular practice, its outcomes as formal attributes, or its aesthetics as trends derived from its applications. What seems to be less critically addressed are questions concerning the role of data-informed and data-driven processes employed in digital technologies as they relate to human input and assessment. Scalable digital processes is structured around the integration of three concepts that aim to augment the architectural discourse around the topic of digital technologies beyond any singular definition of its term. One, the synthesis of work across scales rather than an isolation of disciplines. Two, the ability for digital platforms to perform as generative instrumentalities rather than applied tools. And three, the methods or approaches that dictate various processes. Tonight's speaker, Fabio Gramazio, architect and co-founder of the architectural practice Gramazio Kohler in year 2000 with his partner Matthias Kohler, engages fabrication research through multidisciplinary interests ranging from computational design and robotic fabrication to material innovation. Gramazio received his architecture diploma from the ETH in Zurich in 1996, where he is now professor of architecture and digital fabrication since 2005 and director of studies since 2017. He also is co-founder and board member of ROB Technologies AG since 2010. Gramazio and Kohler have lectured throughout Switzerland and internationally, including England, Germany, Italy, France, Brazil, Serbia, South Korea, and in the US at Princeton, Penn State, University of Tennessee, to name a few. Their numerous award-winning designs for technology and innovation have been fully realized. Current projects include the design of EMPA Nest research platform, a future living and working laboratory for sustainable building construction. As professors, Gramazio and Kohler developed the first architectural robot laboratory at ETH Zurich. The ensuing research has been highly influential in the field of digital architecture, setting precedents and initiating a new research field focusing on the integration of industrial robots in architectural design and construction. They have contributed to numerous exhibitions around the world, such as 2008 Architectural Biennale in Venice, the Storefront Gallery for Art and Architecture in New York in 2009, Flight Assembled Architecture at FRAC Center Orleans in 2011, and Rock Print at 2015 Chicago Architectural Biennale. Their recent research is outlined and theoretically framed in their book, The Robotic Touch, How Robots Change Architecture, among their many other publications. Tonight, his lecture based on his book introduces a new way of thinking about materializing architecture. It brings forward key implications of robotic fabrication in architecture and presents a selection of projects that have originated over a decade of research at ETH Zurich, ranging from the non-standard brick facade of the Guttenbein Vineyard to the recent rock print installation at the Chicago Biennale. With this scope, the lecture proposes a digital building culture to unfold its contemporary and most apt constructive expression through the amalgamation of digital logic and novel machinic processes. So please kindly silence all your mobile devices, and please give a warm welcome to our guest, Fabio Gramazio.
Well, thank you, Naomi, for the kind and extensive introduction. Thank you for inviting me to give me the opportunity to lecture here. I will use the next 45 to 60 minutes to give you an overview on, as Naomi said, on what we did, not only the last 10 years, but also 15, almost 20 years, through all the new projects, through architectural build work and very speculative, installative work. I would like to start with the title of the lecture, that is Digital Materiality in Architecture. And this is a concept or a definition we coined almost 10 years ago when we published a book about this called Digital Materiality in Architecture. And the reason to do this was that we felt that these two categories, on one side the digital, that for us, for Matthias and myself, was sort of a familiar thing. I need to give you a bit of background. Matthias and I belong to a generation that doesn't have a name, but exists, and is characterized by the fact that we were around 15 in 1985, and back then, for a few years, machines, computers that were suddenly cheap enough to be given to teenagers as toys. And I'm talking about Commodore 64, 21, all those things. And they were still primitive enough to come without a desktop, an interface, a visual graphical interface. So this machine, the only thing you could do were to program them. And the consequence of this thing, this maybe lasted 2 years, you know, was that we learned to write code in a very playful way, you know, long before studying architecture. And this sort of instilled in us this sort of confidence that we could manipulate data, that this would be just sort of a foreign language. And that this language was pretty fun and much easier than other languages we're learning at high school. You know, French, German, those are more demanding languages than BASIC. You know, BASIC was the language used to program this machine. And then 5 years later, we studied architecture, Matthias and I, and we discovered the world of architecture and the world of materials and of space. You know, the education at ETH back then was very much traditional. We had computers in the lab, but all the rest was done manually, drawn by hand and so on. So these two worlds, these two cultures that for us felt very similar, very close to each other. We didn't see any contradiction between those two activities. To program was on the level of the intellectual activity very close to design. And it was about it is about organizing things, creating hierarchies, defining processes, and so on. But for a long time, and I'm talking about the whole 90s, these two categories didn't find together. They felt being antagonists. You know, you had the analogs, you still have them, you know, but then it was really a dramatic phenomenon, and the digitals. So the people, basically this came down to the question, do you engage with computers or not? You know, and we were convinced that this relationship between those two domains was of much more fundamental nature. And basically this term where these two worlds are sort of juxtaposed and brought very close together expresses this wish for a change in architecture. And the consequence of this, let's say, long period where we were designing architecture, or pretending that we could design architecture with computers, or use computers to design architecture, but we're not able at the end to materialize things, led us, this was around 2000 when the first big machines were coming out, were becoming available. Think of big CNC routers spread throughout the industry, in the timber industry, but also in others. We felt that it was, the moment had come to revert the equation. So for almost 20 years, we had been preoccupied with digitizing everything, you know, not just in architecture in general, but also in architecture. It was about getting rid of the paper and bringing the data into the computer, digitizing the information. And with the advent of this machine, we could look back and say, okay, if we have all this wonderful data and we are able to work with it, to manipulate it, to design with it, then we should now investigate very carefully how we could get this information out of computer back in the physical reality again. And in order to illustrate with this in a very literal way, I would like to show you a very old project. This probably was one of the first installation we did in the architectural office, 2002. It was a research project outside of academia called M-Table, for mobile table. It was a table series that could be designed by the client, directly by the client, by using a mobile phone. This phone, they're pretty old in the meanwhile. I think you are too young to know it. But this was actually the first smartphone. The term didn't exist yet, but it had all the components of a smartphone. Not the touch screen and those things, but it could be programmed. So it was a full computer. It had a color display, very, very low bad resolution, and it could even load apps. And also the term app didn't exist. You know, it's sort of a tragedy of history. Nokia that went out of business because of Steve Jobs, and the app already had the app, but the marketing department didn't know about it. You know, but they had it, and we used this and created an application. And this movie shows you how it worked. You could distribute points on a surface. Then with the physical pressure of your thumb on the joystick, apply pressure on these points, and the pressure would deform the surface, and the deformation at a certain point would create a hole. When it's a very simple geometric operation. When one surface cuts the other, you get a hole. And this was the only manipulation you could do, and then you could choose color, size, and so on, and submit the design to our server, where what you were submitting actually was this parameters. This is human readable, more or less, if you have seen the logic. So there is authorship, there is dimension, there is color, and there is a few points defining these points on the surface and the magnitude attached to it. So it's a very, very reduced amount of information for a very complex geometry, this doubly curved NURB surface, that with this pieces of information and the algorithm being the design or the rules of the game, or however you want to call it, allows you to rebuild this geometry. And this geometry can be directly, through a further simple translational step, sent to CNC router, and the CNC router transform this information into material and outputs a table that you see here, one of the infinite possible instances or variation of this table. That is a very irritating object. At the same time, extremely elegant, but also extremely dysfunctional. You know, a table with holes is sort of problematic, you know, because the hole undermines the function directly. It's very aggressive. And additionally, the hole, because of this direct link between a design act on a small, cheap, low resolution device that is not even perceived as being a computer, you know, but is a gadget, a phone, is directly linked to a physical output. So there is no intervention of a professional, you know. All these decisions are delegated to the client that doesn't have the education. So you see, this project is instrumentalizing technology to ask very fundamental questions, at least that were very fundamental back then, and in my mind still are unanswered. And the questions are, what happens to authorship? This is one of the questions that this project asks in a environment where, you know, suddenly things get partially automated. You know, other stakeholders can intervene much more seriously into a design process. You know, so who decides what parameters are open to whom and why? And this last image shows nicely, and this is just a cutout of the hundreds of, 9 tables were produced and sold. This was a limited series. But these tables here were designed by who knows who, you know. Some of them are beautiful. Some of them have been designed probably for hours, you know, people speculating with buying one. Others are just a few clicks. Some are, as I said, elegant, some are ugly, some are functional more or less than others, but they all share one common thing. They look almost the same. You know. And here two questions come up. One is this, let's say, opening up, you know, questioning our role as designers, you know, because to delegate decision on form is pretty radical, still is. You know, we are educated in a way that tells us that shape, form is our domain. And what this project proposes is to shift the control on form up one level to the control of processes. You know, we are the authors of the author of the process. You know, so do we really delegate authority on form? This image questions it. You know, and if you look or ask the question from the other side, from the side of the supposedly free client, you know, you could argue that this is fake freedom that we give the client. So the project is asking a lot of questions and giving little answers. Now, as I said, these questions are still actual for us. And the question that follows up is, and that is very much at the core of what we do, at least in our practice, is programming meaningful? Or what is programming? What does programming mean to our profession? You know? And as I said, but this is sort of a chance of, you know, a biography. We learn to program as kids, but we're always confronted with the question, should architect program, yes or no? And I would like to answer to this question showing a project that is a bit more recent. And I won't talk about the project, but I want to show two aspects of this private house. And in order to do this, I quickly show you where it is. It's in a village nearby a lake, very nice, but also very protected, difficult situation. This is the mass plan. And I'm showing you this because the first issue I wanted to address is about the shape of this volume. You see, it's a rectangle that has been cut twice. So two edges are missing. Now, the question is why? You know, is this a design decision? Do we like the shape? Yes, no. As so often in architecture, these things have a reason. The reason is very simple. If I show you this, you have to know that the house here, to know two things. The lake is here on the left, not in the image anymore. And the small rectangular house there is the house of the client. So you have classical situation. Client is building in its own garden, second house. Now the parameters are very clear and simple. How do you place a volume that is as big as possible without compromising the view of the old house? You know? And this is a trade-off problem because, of course, you could cut down this house in several ways, but there is one cut that is sort of optimal because it's not big enough to compromise the internal organization of the new house, but still giving the old house a certain view, so keeping its value. So you can reduce this problem to one angle. You know, if you make it bigger, you get this. If you make it smaller, you get the other thing. And the second angle has a similar reason, but it's not view, it's accessibility. So you have to drive in with the car that you want to park in the back, blah, blah, logic. And it's also an angle. This one is a bit more determined because you can calculate what the radius, you know, a car needs to park is. Then you have to choose on the size of the car. So this is a parametric problem. You know, this is a computational problem. Now, it's a parametric problem, but it's not necessarily a computational problem. You know, you could write a program, it would be pretty easy, that does this for you. You know, but we didn't, and nobody would do this. And why? It's because to iterate this question, you know, these two angles on paper, in your mind, while sleeping, while showering, is pretty easy. You know, you can do it so often that you will find the solution that is optimal for you and for the client. You know, but in principle, it's a parametric question that you would formalize very easily and have a computer calculate it for you. Okay. Now I quickly show you the section of the house. It has a pitched roof that is cantilevering on 4 sides. It has a window, you see it here, on the first floor that follows the roof line. And it has, you see it, it's not that visible here. The whole facade is covered with vertical wood slats perpendicular to the facade. This has reason, legal reason, because this amount of glass this house has wouldn't be allowed to be exposed directly. Now on the left you see how this house appears from a certain distance. So it's a homogeneous closed volume that from the inside, of course, is completely open, because from the inside you don't focus on these things. And on the left, on the right here, you see something is strange. So there is some manipulation, some work that happened on these things. And this image shows you what has been done. These wood planks, slats, have been milled on 2 sides symmetrically at certain locations, so they have been slimmed out. And this cut, you see it down here, is not always perpendicular to the sides, but can be inclined. So what is happening here? Again, it's a parametric setup. You know, it's about perception. It's sort of an engine we build to ourselves in order to be able to control view. So to control the degree of opening, because if you have slats and you slim them out, then you just open the field of view to the side and you create sort of a lens effect in 2 directions. And with this angle, you can control to which side the view opens up more. So it's a setup that allows you to do very traditional architectural operations that normally are about what you see, what you don't see, about orientation, sun, exposure, privacy, and so on and so forth. Now the problem here, because you could argue in general terms, this is exactly the same issue as the first one I've shown you. You know, you can write a simple equation that tells you what the relation between this geometrical manipulation and what you get is. The problem here is that you don't have 1, but you have 315 elements. And 315 is not a lot. You know, it's a small number. But if you think of designing, modeling 315 complex elements that are all different and all dependent from each other, so if you change one, you have to change them all, you know, then you will end up very quickly with numbers that you cannot manage anymore. You know, you end up very quickly with years of work. You know, if you want to do what design is to iterate. It's about doing something, observing what it does, and redoing it until you are happy with it. You know, so with only 315, you get stuck in a dilemma. You know, because you can imagine and write down, you know, your rule. You could tell to somebody, to a friend, to the client, it would be great to do it this way, but then you cannot do it unless you program it. You know? Because now to formalize these rules that you define for yourself and to have a computer executing them for you, you know, becomes very powerful. And it's the only solution you have to be able to to do the design that you have in mind, you know? Because suddenly all this geometric operation are taken over by the robot and are iterated 1,000 times a second, you know? And you are the one that decides on the rule, changes them, you know, and then at the end decides what you want to build. But you have a second problem, you know, and now we go towards, again, machinic digital fabrication. Even if you have written the program and at a certain point say, yeah, this is what I want, now you have 315 files, you know, who does it for you? You know, if you want to have to print out 315 profiles and giving them to contractor, he will do it, but this will be way too expensive. You know? So you have to find a fabrication strategy, you know, that allows to capitalize on the data you already have, you know, and to transform something that is, if you do it manually, you know, very complex and time-consuming into the most simple thing you could imagine. And this is through this very simple machine. This is a machine that is very common in the timber industry. It's nothing else than a rotating blade that moves along, or in this case, is stationary, but the wood timber slat is moved along it, and it can be moved in the Z direction, so in height, and tilted. So this machine is exactly doing the two, or performing the two design parameters you were working with. So there is a direct link between these two things. And this allows you to just send the slats that would anyway go through this machine. Because when you order 315 slats, you know, and you say, I want them 20.5, you know, it's very unlikely that somebody has the 24.5 in the backyard. So they will have the 22, and then send them through this machine just with one value on the machine, straight, you know. Now, what are you making? What are you doing? You're doing the same process, but instead of giving them just one Z value, you give them the whole profile. So you're doing something the machine is already able to do, you know. You're just adding data. You don't add time, you don't add complexity, you don't add handling, you don't add anything. You know, and you end up with this very simple, in the end, facade, you know, that is completely controlled by you as a designer. So there is no random in this at all. That is, if you think it through, for free, you know, because if you would have done it without this manipulation, so without taking advantage, you know, of this process, it would cost exactly the same amount of money, you know. Okay. So these were two projects sort of from the early times that I used to explain what programming and parametric or computational design means to, or should mean to us architects, where the potential is, and also when it's meaningful to use it and when it's less meaningful. Now the next question that was already implicit in this first table project is, but it's becoming very, very important right now, you know, with the whole question about labor, about automation, about artificial intelligence. The question is, can the author, the concept of the author, coexist with the machine, you know, with the robot? And in order to introduce this, I would like to show this image. This is the first robot we built in 2006. And it's carrying a collaborator of us on the end effector. Of course, this is extremely forbidden. This is not a production image. It's an image by an artist, but it's an important image because it's depicting something we think we should discuss more. And it's about the relationship between us and the machine beyond the categories of labor and of automation and of performance and so on that are normally driving these discussions. And we strongly argue that the relationship, that for a long time, for about 200 years, has been a conflictual one. And this is the history of industrialization. It's the machine getting bigger and bigger and bigger, more and more expensive, not being owned by the craftsman anymore, but by the capitalist and so on and so on. You know this history, that now could theoretically, because there is also another narrative, but it could theoretically, if you look at it like this, be switched back, to a relationship where we can be, when I say we, it can be the designer or the craftsman or whoever, get control on a very, very complex tool that is not questioning our existence, but augmenting our potential. So allowing us to do things that we be able to do without the machine. But to understand the machine in this way needs to reconsider this very established rhetoric of conflictuality that we sort of instinctively, bring up when we think about the machine, because the machine for a long time has been there to substitute us, to get us out of the process, because we have been considered to be a source of cost or a source of risk or a source of imprecision, whatever. And in order to quickly explain how we read this relationship in a positive way, I would like to go back to this very first, the brick. And this has been the very first material we used to work with our first robot for a strategic reason. It's a proof of concept, a machine that can place something in three-dimensional space. And what do you use? You use the oldest building block that has to be placed something in space and see what happens. So you see a brick wall is a stretcher bond. And the question is, how do you describe a stretcher bond? You could describe it like this by drawing it. This is done in architecture to represent, in an abstract way, a brick bond. But this is not so practical. Let's say for execution, probably you wouldn't give this to the building site because you don't expect any mason to make small crosses and say, this one I have placed, let's go to the next one. For the building site, you use this description on the right, because it's enough to define what element you use, the size of the final wall, and to tell somebody that you want a stretcher bond, and then everything is clear. This is a very compressed way to describe this thing. This has been done like this forever. Now, if you want to communicate this to the robot, you do a similar thing. You write a program, and this is on the right a program that does exactly this wall here. I don't know if you're familiar with the basics of programming. You have control structures. One of these is a loop. In this case, a for loop. For loop repeats something, an action, over and over again until a certain condition proves to be true or false. This is up to you. And the trick here is that two of these loops nested one into each other are equivalent to the wall. Now this for you is very abstract. This is not abstract. I could probably ask each one of you to build a brick stretcher wall here, and you would be able to do it. And you would perform exactly what this program does. You would do a row and then go up, shift by half a brick, and repeat. And repeat these two very simple rules until you have reached your goal. OK, the computer can read this. But this doesn't make so much sense, because with this definition, it's so easy to execute it for a human. It starts to make sense if I bring again the human into the equation and say the human has the ability, now in this case, to understand the material, beyond the stretcher bond. So it can depart from a stretcher bond, but then it can start to test empirically what manipulation, what changes could be done on a stretcher bond, to what extent something can deliver, or a certain distance can be variated, and so on and so forth. And then, in this case, he wants to do a rotation. He can add this rotation into this very simple program. And the rotation can be depending on the last brick, depending on the position in the wall, depending on the position in the row, whatever. Now, what happens if we do this? Following happens: that this program produces this data on the right. And this data on the right is so small that you cannot read it, because each single brick has its own information. In this case, it's an individual rotation. And suddenly, what before was a very efficient way to communicate a whole finished thing to a human, that just knows the rule and executes it, and because each brick is the same, has the same position, just shifted half a brick, this can be done without complex helper tools or measuring tools. Now here it becomes very, very hard, because each brick has its information. You have to measure it in, And now the nice thing is, if you go back to the relation human-machine, that exactly this information is exactly what this machine expects. You could give this machine the same position 500 times, the machine wouldn't make the difference. For the machine, it's absolutely the same. So what we are doing here is to directly connect the ability of the human to design a rule, for example, to experience the physical world, and to formulate a material idea, with the ability of the robot, of the machine, or of the computer to execute this thing. And you couldn't switch this to images, because the machine is absolutely not able or built to do this operation on the left, and the human is very, very inefficient in doing what the machine does. And the result is this, a very simple thing. This is just each single brick is rotated in a specific way. And this is where we see the emergence of what we call digital materiality. It's suddenly when two realities, start to interact in a way that you would not expect, while each one has its definite, recognizable appearance. You have a material that is familiar, but organized in space in a way we would not do as humans, just because it's not natural to us. Okay. So the next question is, departing from this, can the digital alter material presence? What's the difference between organizing 30,000 bricks with a stretcher bond logic, or to design a logic that is more complex and can be executed by machines? And in order to test this is 12 years ago, we had the chance very quickly after this first proof of concepts to realize a facade, a big facade for a winery. Here you see just the design concept. that we set up in order to get the information for this 300 square meter of brick facade, informed brick facade. We interpret the winery as a basket. We filled it up with spheres of different dimensions. And then we looked at this synthetic content from parallel from the full facade and transferred the color information to the rotation of the brick. And this gave us individual position for each single brick. And with this very simple process where the robot picks a brick at the predefined position, then applies epoxy glue, adhesive. And this is very important. This is done by the robot because each path is individual. You know, it would be almost impossible for a human to do this in a reasonable amount of time, and then place it on the brick. So it's a sort of very low resolution 3D printing process because it's nothing else than putting the material where it should be. And then the rest is simple prefabrication technology, so the transport and the setting in place on the building site. And the result is this one, where you have these elements now that are all individual. You know, you have this information that is conveying that has different scales. If you are close by, you know, you won't see the big motif, you know, but you see this fields, these movements. If you have a certain distance, you recognize the image, but this image changes, you know, in time continuously. So virtually it does not exist, you know, because it's entirely dependent on the position of the observer and the position of the light source. So the time of the day, of the quality of the light, and so on and so forth. And if you look at it from the interior, you have, with the same physical data, you have again another information, because here it's not the reflection on the light creating the impression in your retina, but it's the distance between the gap that is modulated by the rotation. You know? And if the gap is chosen in the right range, then our eye is sensitive to this contrast that can read this effect. Okay, so you see a very simple process that leads to an architectural, very sophisticated effect and result. Now, very, very quickly, to show you another example that is more recent, also working with very simple elements to create a very complex result. I would like to show you a ceiling system that we developed for this building. This is a building we designed a few years ago, an experimental building platform. And for the interior, so this is a very rough building from the exterior, and in the interior it's very, very refined. We developed this ceiling system where very, very lightweight, this aluminum cylinders, this is like beer cans, you know, from the amount of material. They're just stiffened out by this border, are stacked in elements, you know, and the only information that is added to this grid is the Z position, you know, the depth. That is just shifted by 20 millimeters, you know, from the center lines. And you end up by gluing again these elements together with very, very lightweight parts that are individual, customized, and can be aggregated, you know, to a whole, to this ceiling, you know, that is basically a landscape, you know, and the amount of material is absolutely minimal, you know, and before informing them with the robot, it's just a mass product, you know, identical, thousands of identical cylinders. Okay. The next project expands this technique a bit on two levels. This is called the Sequential Roof. And this show you, start with a movie of its fabrication. You see here a robot takes a timber slat, 5 by 10, so pretty slender, and processes it by cutting the two ends. And in the second step, it lays the singular pieces down on a bed, on a table, you know. So again, it's a stacking process. It's like the aluminum cylinder or the brick, but on a bigger scale, on a structural scale, and with a processing of the element in the process itself. You know, through these two cuts, all these pieces are different, you know, and allow you, in this case, to build very big, this is 15-meter long trusses, you know. Again, custom, individual, load-bearing, that are prefabricated in the shop, installed with all the needed subsystems like sprinklers, light, and so on and so forth in the shop, you know, where everything is very easily accessible, and then transported on site and craned the same way as the brick elements in the winery have been craned to the right place, and they're just fixed with a few screws. So what you observe here is, if you think that this roof is 2,300 square meter, so this is 23,000 square feet, and is made out of 50,000 singular, individual, different parts that have a very precise position in space and are nailed together, you know, with a certain amount of nails that have to be in a very specific situation. And all this complexity is handled by robots in the shop. And what comes to the building site is just 168 elements that have to be placed at the right position. And here you see the final result. So you have this landscape. There is not, in this case, like in the winery, a filling of structure or something hanged to a structure, but the structure itself, you know, with all the complexity that comes with being a structure. Here you see the nails. You know, we have almost 1 million nails in this 1,300 square meter, 2,300 square meter of surface. And all these nails have a very specific position, you know, because there are norms that define very exactly how far two nails can be from each other, how far from the edge of the element. And in this case, because it's a stacking, a nail always goes through 2 layers, you know, so in one layer you always have the nails of the 2 neighboring ones that meet, and they should not come too close to each other. So here you see that, again, to design such an architectural element, it's about programming it. So it starts with a definition. Here you see sort of a model that overlaps all the different degrees of information. It starts here down on the right in defining what the logic of the shape should be. Here the logic was pretty simple. It was about water, you know, that should be evacuated only through the big columns, you know. So this should be the lowest points, and this has informed the surface. Down the line, you know, where all the subsystem and the position of each single nail is defined, you know. And the whole process doesn't produce one single drawing, you know, one single plan, because a drawing wouldn't make sense in this context. This is the only plan existing of this building, you know, and it's a representation of more of a concept than of the architecture itself. It's representing this incredible amount of elements that at this resolution looks like a fabric, you know, like a textile. And you see that it also behaves like a malleable textile, where, you know, you have these white openings, you know, you have the light openings, but also you have the big one, the light. This is the staircases, and on top of the staircase, you know, you need to evacuate the, you know, I don't know in English, the smoke, you know, fire case. And normally you have to cut through the structure, you know, and here is the structure that goes away and creates the space for this subsystem to exist. Okay. The last question is, after this very, I think, very precise and architectural and applied project, I want to show a few very experimental ones, you know, questioning what materials systems could be in the future. And one question in this regard is about dynamic material control, or about control in general. So is the future about dynamic material control? First project is called Remote Material Deposition. This is an installation we did a few years ago, questioning the, you know, this idea that architecture could be 3D printed. That is around since 15 years. It's an interesting idea that has a few problems, and the biggest one probably is that it's a direct scaling up of a process that we know from product design, you know, where normally the machine is, or let's say the product is smaller than the machine. If you apply this to architecture, you very quickly run into the problem that the building or architecture is big per definition, and if the machine has always to be bigger than the part it's printing, this doesn't work. So we suggest that in order to solve this dilemma, instead of building a huge machine that prints the architecture, we leverage on the dynamic control, meaning the capacity of a small machine, like in this case, to very precisely shoot material through space. And of course, this has a long tradition, you know, so ballistic curve. It's something we know since a long time. And so we can calculate where an object should land if you give it a certain kinetic energy in a certain angle. And also the second principle of such a process is familiar to us, the feedback. You know. And at least in military technology, since hundreds of years, we know that in order to control such a system, we need somebody observing, you know, what happened with this equation we have seen before, because this is the place it should theoretically land, you know, but actually, because of wind and many other factors you don't fully control, you know, you need somebody to observe if you were too long or too short, you know. And this is exactly what feedback and control is about. So for this project, we implemented this loop where a machine shoots mass, in this case it's clay, a scanner mounted in the space gives three-dimensional back three-dimensional information about what happened, and this information informs back the 3D model and the next step of the process. So here we built, very literally, we extruded this clay projectiles. We mounted a scanner and this machine in the space. Machine is nothing else than a robot orienting this pneumatic shooting device. And here, you see, we had a blueprint of the structure. We knew where we would like to build things, but how this would exactly happen was a dynamic process of continuous, correction going on, And also the final result, if you look at this structure, where that for us has an incredible beauty, Here the element itself, tells the history of its own making. You can look at it and you can tell which of this cylinder impacted from which direction, at which speed, And we are able to do vertical things. This is the nice news, And as soon as you're able to do vertical things, you create architecture. And here you see this launching is absolutely out of control, because you have no chance to tell, how this part will land, There is this let's say, this part of the process that is out of control, that is generating much of the fascination in the work itself. And the second project that is a bit more under control, but still very much subject to a, let's say, a material behavior is Rockprint. Rockprint was an installation we did for the architecture, the first architecture biennale in Chicago 3 years ago. And Rockprint is leveraging on a physical principle that is called jamming. Jamming is what happens if rigid parts are brought into a situation by boundary condition where they cannot move anymore. So there is nowhere they can break out. And when this happens, then the whole compound becomes solid. And if you change the boundary condition, then this process is completely reversible, and what was solid becomes liquid again. And this is called jamming transition. And you can see that this process is very much depending on the geometry of the elements. Cornflakes work very, very well. You can try to do it with sphere. This will be less successful, And one thing that works very nicely is gravel, so rocks. Rocks have a geometry and a surface materiality that is very good for that. So what we proposed here was to design a sort of a printing process where not the material, the aggregate would be printed, but a string would be deposited in layers, carrying the information about the final geometry, because where the string would interface between layers of rocks, the string would create or favor the jamming condition, where the friction between the layers would avoid the stones to break out at the surface and to generate this chain reaction that then would lead to the collapse of the whole thing. And this you see in a very tedious process, layer by layer, in this venue in Chicago that was by chance an old library, so the floors were very, very strong because this is 2 tons of material on sort of 1 square meter of floor. Were printed, and as you see here, after the process was finished, this containment formwork was removed. When this was removed, the material started to collapse, and the material, because this is already a jamming phenomenon that you see here, and then the material that was not jammed by the string could just be removed by bringing it to collapse. And at the end we had this very strange column sculpture tooth standing there, where the shape was of course a direct reaction to the material principle. So it was about bringing the material as high as possible in order to create all the pressure we would need to create a jamming in these very slim columns supporting the whole structure. And here you see just close-up of the materiality. Again, it's not under control, and this is the beauty of it. You know, it's the material system, material logic expressing itself on the surface. And the very nice thing here is that, and this was then instrumentalized in the finissage, you know, is that it's a completely reversible process. Here it's literally, you know, if you rewind the movie, you know, because you just put the pulley on the ceiling and pass the string through and then rewind it into the big spool. And the raw materials that you had in the beginning, that was just uninformed string and a pile of material, you know, and this is how you find it in nature. This is how gravel aggregates, you know, if you just put it there. Is the back to the starting condition. Okay, and the last quickly project is now going 1 step further. You know, here it's about speculating on aerial construction. You know, and this is not shooting anymore. It is saying, what if the machine, you know, wouldn't need any physical link to the space anymore, but would be a flying machine? And we started by doing experiments. Pretty naive experiments, finding out what such a machine could do. Could the machine aggregate sticks? Could several machines work together doing this? And as you see here, we found out that this is pretty demanding and complex, you know, and that probably it's not the best thing you can do with flying machines, because you're not really exploiting, you know, what the machine can do best. And so in the next step, we developed this process here that is nothing else than give the machine a spool of string that can be unrolled while flying, and have the machine perform sort of a spatial weaving, you know, because what this machine, because of their size and precision in flight control, can do is to fly through a structure. You know, this is a robot cannot do, a human cannot do easily, you know. But this machine can do it in a perfect coordination, you know. And you see that here the challenge was to build a bridge between these 2 structures, you know. And here you see the beauty of these coordinated movements, you know, that they are both extremely demanding and complex, but also natural. And this anticipates a bit, you know, what could be probably possible in the future. You know? And again, here it's nothing else than feedback and control. You know, drones are about feedback and control. Good. And this project has been inspired by a project that is a bit older, and I use it to conclude because, again, it questions a bit the notion of how architects should instrumentalize technology. And probably this will be the subject of the discussion we'll have. As you know, flying has always been a very important driver to architecture. And here you see a drawing by Archigram from the 60s. So this going beyond gravity, being free to place things where they should be, also maybe temporarily. And for an installation we did for the FRAC Center in Orléans in France, we proposed to use drones to do a 1:100 model, to build as a performance 1:100 model of a big, huge structure that you see here, a 600-meter high tower, a vertical city or village for 30,000 persons, whereby these elements would not be containers, but they would be 3-story buildings. So it's really rebuilding the city, you know, with 3-story building and just stacking everybody on top of each other. And the method here has been twofold. On one side, you've seen these renderings and these drawings and these volumetric studies. We really analyzed in the tradition of ideal city planning that since Renaissance pops up every few hundred years in a more or less virulent way, you know, and it is always about imagining a future, being fully aware that it's not there yet, and maybe it will never be there, you know. But if you look at this project, they always are very carefully thought through. There are long description and wonderful drawing about how things are built, with what material, with what processes, how the social system around works, the politics, and so on. And we did the same thing. But at the same time, in the same space, in a complete different tradition, that is a tradition of performance art, you know, it's where you say, we will build a model of the same structure that is ideally depicted on one side of the space, you know, a 1:100 model, completely automatically built by drones in between the people, you know, during the exhibition. You know. And the nice thing here is that these two opposites, you know, that very much relate one to each other. So you have this imagined future, you know, and it comes nicely, naively, you know, it's like all the others, and you imagine this thing. But in the same space, the future is already here. Of course, it's model scale, you know, but these machines are doing it autonomously, you know. And there the question is a bit, what is the relation between reality and utopia? You know, what is the relation between reality, you know, or what we think is the technology that we have at hands and the technology that is yet to come. Okay, this was the projects, maybe as just to sum up a few concepts. So we think that in the future, if we leverage on this cultural systems, because I call them cultural systems, programming and so on, then material becomes informed, and this independently from the material, raw material itself. So it's not about high-tech material, it's about probably using the material we have at hands, but making them more performative, more beautiful, more intelligent, and so on. Then the second thought is that this asks us, or gives us the opportunity to rethink construction. You know, we don't have to, but there are moments where new things are possible. Very important is we should get used to think in categories of processes as being the result of a design process. So processes that then lead to form, but not to one specific one, but to a whole family maybe. And this is not giving up, this is not anything goes, but it's a very precise, act where we believe that this will give our profession consistency again. Will probably, if we do it seriously, bring us back in the center of the construction process. And last but not least, and this is very important because instinctively there is the tendency we all have, if you think about the digital, we think about, and it's a big misunderstanding, we think about productivity, efficiency, BIM, and these are all pretty rational concepts. We're convinced that digital materiality can bring sensuality back into the architectural discourse at the very core in the material itself. And this is very good news for us designers. So that was it. Thank you very much for listening for so long. I think that we have still time for questions, right? Should be, yeah. Thank you.
Thank you so much for that excellent lecture. We have a few questions that we prepared to start off Q&A, and then we're going to hand it over to the audience.
Yeah, thank you, Fabio, for the great and inspiring lecture. So I'm sure there will be a lot of questions for the audience, but we will start with a few questions just to start the discussion. So the first question, it's about mass customization and standardization. So with the pervasive digitalization of processes, materialization and material practices become again an important parameter of architecture and design. So material and digital practice. As the digital is more and more grounded into tangible and material practices, as we have seen tonight, and I think this is also part of some of the questions at the beginning and at the end, and the reciprocity between the two, robotic processes become an icon for the profound reformation of the discipline in relation to construction and manufacturing processes. So could you expand on how do you see current processes of mass customization and how this could potentially affect and change the way in which we see standardization within the discipline of architecture? So the ubiquitous type of uniformity that could, in a way, emerge from those processes.
I mean, this is clearly the result of, or one result of machinic processes. There is no reason anymore to do two identical parts because this doesn't give you any advantage, as it was in a, let's say, serial logic where economies of scale were dominating. This doesn't mean that everything needs to be different, but means that when you decide for the series, this is a conscious decision. Until now, you didn't have to think about why you were thinking in series of something, because this was the logic of, I mean, of course you could go against all these things, and but reasonably this was the cultural paradigm of the 20th century. The whole modernist aesthetic builds up on this, and this is not a free choice. This is just because it is that it is. And now, when this sort of condition falls, you have again to think about what it means to do two identical parts. It's not something that happens just by logic. This is one thing. But I think these processes are ongoing. I'm not concerned. What we propose is to go one step further, is to think of how these logics are implemented. I don't want just the freedom to order 3,000 different parts, and have something delivering it to me. But I would like to be able to design the process down to the material fabrication of it. So to reconnect these two ends, that originally were the same, and then have been. And this means that we have to engage, because the economic logic between mass customization is known, and if we do not engage, others will do it for us. And at a certain point, they will come up with products. And this was the logic, again, of 20th century. So the architect is not open to any craftsman anymore, because there is no, but he's choosing out of a catalog mass-produced objects. Maybe chooses the color or the finish, or it's very poor. And this could happen also in the logic of mass customization. Somebody else deciding where the variation of the product is to be found if we do not engage directly.
This brings to the second question, which is directly related and deals with, I guess, issues of seriality, but it calls to mind just listening to you speak about this, Gilles Deleuze's difference in repetition. So it calls to mind those moments that can be replaced or can be repeated, but are similar but not quite the same. And in digital generative processes, the articulation of architectural morphology for this variation focuses on emergent and adaptive properties of form. And with the emphasis shift of making a form to finding a form that's been so current in the last 20 years, the stable is now replaced by the variable and the singular by multiplicity. So in the projects that you've shown us, just like you to expand a little bit about how your work lies between making and finding a form in this sense.
I would argue that in the 90s, and this was the time when we got socialized architecturally and so on, and this was the time when I would say generation older than ours, experimented with under the influence of Deleuze and so on, experimented with emergence of form, with, I think, of Greg Lynn, animate form, all this software techniques to get to form. We propose, or let's say the whole concept of digital materiality comes out of the understanding that there is a need for a process that is sort of synchronized with the form, so that the form doesn't make sense if there is no production technique that, I've shown you this facade just sequentially, showing, okay, when we had this idea, then we produced this data, and then there was this machine that did it fantastic, but this is not how things are. You have to look about, you have to sort of, with one half eye, look at this machine before even starting to have the idea of, this is what design is. So to think about the potential and the constraints of the material physical world and the processing of physical material while designing is important to us.
So the processes stand between the making and the finding of the form. Yeah, makes a lot of sense.
I think this brings to the next question about digital craftsmanship. And so in the production processes, the exchange between the man and the machine, I think is also what, I think in the different questions that you set up tonight, you talked about the exchange within the physical, the material, the digital, and the man and the machine. So they're both offering, they're both setting up, synergy and complementarities. So how they work together, but also how they work in a way apart. So I'm wondering, what are your thoughts on how we can, or if there is a need for, to embed the agency of the manual crafting within the robotic processes?
I'm convinced, but maybe I'm just naive and romantic. I'm convinced that this figure of the digital craftsman is already emerging, because the digital craftsman is nothing else than somebody that knows about both the material and the technological process, a complex one. And in Europe, timber construction has already done this, because it's sort of a strange exception, in the construction industry is known to be very conservative and slow and adverse to innovation. But there is this exception of timber industry. In a small region, it's Switzerland, northern Italy, Austria, southern Germany, so it's the Alp region that about 20 to 30 years ago was near to extinction because they were doing stuff, that was high price, low quality, had a bad image, and so on and so forth, so very bad condition. And through technological innovation, they reinvented themselves, from the inside out. And what they did was to invest very early in the 80s in software, not just by waiting for somebody else to bring them the software they were dreaming of, but by doing it themselves. So I've created as a byproduct of this innovation project now the biggest worldwide leading software companies for timber construction industry are owned by these, the same companies. Same happened with the machines, the biggest producer of wood, CNC wood processing machines sit in the same area. And now 30 years later, they do high quality work that is recognized worldwide. Shigeru Ban comes to Switzerland to do his stuff, and he even flies it back, the whole building to South Korea if it's needed. It gives a sense of the added value, in the knowledge. Through good marketing in the 90s with a few important architects, they gave their material a complete new image, so from being, and this is impressive, and if you go into these companies, they are high tech, and the people working there, they have a knowledge, practical knowledge on how to work the wood, but they're also able to program extremely complex machines, and it's completely natural to them. And if this is not the digital craftsman, what is the digital craftsman?
No, I think it's not about duality, right? So, but it's about, I think also in the discussion this afternoon, so it's about finding this feedback that in a way, how the knowledge is passed on to the next, and then how things are, working without a duality, but in complementary conditions.
I think they are. It's maybe again this. If you look at how these people work with machines, you suddenly understand that these people are not scared about their own machines. So it's not the relationship between the labor and the big machine. Where I only control one little part, don't have any clue how the whole process works. They are completely under control there of what they do. And also this distinction between the machinic part and the manual part is pretty fluid, because if there is something to do, they just do it because they know how to do it. It's very organic. And this will only become stronger in the future as soon as machines get more awareness of the environment, so less dangerous, with more sensors. I think this is pretty clear. The risk is only that we architects miss to develop the knowledge and the language to talk to these people. This is the risk, because they are doing their job. This is not. But if we, at a certain point, are not able to communicate to them and to make use of the potential that is in there, then we just miss the chance.
Maybe one last question to follow up on the third one. So at the extreme of automation in fabrication processes, for example, the drones that wove the bridge between the scaffolding, robotic instrumentality can be thought of as independent choreography of material assembly. So where do you think the authorship of this kind of craftsmanship is going, or where does it belong now, or where is it heading towards?
I mean, this is a long discussion that we already started in the afternoon. I'm fascinated by the thought that machines can start to have an own agency to a certain extent, and that what we know from computational design techniques, where at a certain point things emerge that were not there before, and that surprise us, that this could also be extended to the physical realm. But as for now, we are, but this may be because we are still very architect, so very influenced by the fact that although we mix all these things and we say there is not a clear sequence of steps to follow, and that you have to know this at the same time as this, but still we know that if you want to build things, we need a blueprint of them, because we have a client that wants to know what's coming out, and we have authorities that need to but maybe this is just a limitation of our generation, and from the fact that we do this research, but we also practicing architects, and there it's, I mean, many things that we do are already beyond the edge of what is normally done or tolerated. Yeah. But in the future, I think this is it's nice nice possibilities.
Some questions from our students, faculty.
Hi, thank you very much for your fantastic presentation. I specifically remember the first M table that you presented, that I remember you presenting about 10 years ago, and it's still in my mind, and I really enjoyed that being presented again in the context of the larger presentation. Just in continuing the discussion about the blueprint, in a way, if you were to have an ideal situation where you were educating future architects, how would you fundamentally change the way you teach architecture students?
This is a big question. I mean, we are confronted with this question every day. Having young students that have, on one hand, to learn to design. This is the first open question: what is design about? How do you teach it? Then you have a whole range of notions of knowledge that you have to acquire. And at the same time, and this is needed. You can make without these experiences. If you don't know certain things, you cannot design. And at the same time, we want to tell them and give them the confidence that in the future it will be more important to define rules, so to be able to program, you know, or let's say it's not about programming, but if you want to think about design, not just in terms of defining one geometry, you know, but design the rules that lead to this geometry, then you need to master certain techniques that can be very simple but also become very complex. And how to bring this all, you know, under one umbrella is a huge question, you know, because time is so limited. You know, we experience it every term. You know, you have an analysis, then you have to land somewhere, and these are processes that take years. You know, it's about. But this is a general question on our educational system. You know, can this go? You know, be so efficient, you know, as we would like, or are these longer processes, you know, that take that need more space and more experiments, you know, where you have just to do things wrong once, twice, in order to understand what they mean to you. So I have no clear answer, but I think probably the most important thing is to give young students quick success moments, you know, where they do not see these things as duties, so should now have to learn programming in order to, and so on and so forth, you know, but wow, this is powerful, you know. I don't know nothing about it, but it's powerful, and the fact that it's power, that I experience that it's powerful, motivates me to dig in deeper and deeper. Yeah.
Great, thank you.
Thank you so much for your lecture. I was interested about some explanation about if exists what is the relation between the research that you make and the didactic plans inside your school. So if exists some structural plan of education that puts together your research, the research that your group make now, and the study in architecture or engineering or other kind of field. And this is the first question. The second, I was interested also to understand what is the relation between the research and the company of technology that you use. What's the feedback about your work? Is only speculative research or become some patent and so on? So didactic and company in the same time. I don't know if it's clear. Thank you.
Yeah, I maybe start with the second one, with the company. This is the question: how do these things transfer into industry? Yeah. And we have a twofold strategy there. We have research projects. I mean, one clear transfer goal is to educate people that are able to go and work in this company, bring value, but also interface with these companies from other positions. You know, this is mandatory, because without the people, you know, you can have all the patents and machines around that you want. It doesn't work. Now, on the level of the research project, we have very applied projects, you know, like the whole timber research and so on. This is very much interfaced with companies. You know, it's about looking into possible processes they could use in the future, but also looking into machines or processes they already have, you know, where they feel that they do not exploit the full potential of it, you know. And on one hand, and on the other hand, we we do very speculative work, because we feel that this is as important as the applied one. You know, because if you don't radically look into the future, you know, you will get stuck in a circle of optimizations and things like this. There is also a bit the you know, it's a cultural issue. So where do we get the money from? Our money comes from the taxpayer. So where should we look at? You know, and in Switzerland, we can clearly not compete with industry. You know, if you would do only applied stuff, then other company could come. You know, IBM could come and Siemens could come and say, "Wait a second, you're doing what we normally do, but we get money for it. You know, we sell this thing." And in the Asian context, it's the inverse. You know, in the Asian context, if you do research, you are asked to do exactly this. They don't care about, you know, you competing with industry. We have been doing research for years now in Singapore. You know, this is very, very, very different. But you also want these things to happen soon. You know, so it's about the balance between these, and also on a personal level. You know, I think you need, as an architect, to look into things that are not there yet and probably also unlikely to happen. You know, why not? And the second question about the influence on the curriculum, this it relates to the question before. I mean, in doing these things in the bachelor is hard, because, as I said before, at least in our school, we have a very clear methodology, you know, on how you in the first few years learn about. Now, and this is the thing we try to implement, is to start very early with programming, although my personal opinion is that programming should be learned at high school, you know, because it's sort of basic cultural knowledge, you know, of our century. You know, if you don't, but this is another political discussion. You know, we are educating our elites where only 1% and less has a clue about how our world works. You know, and this has never been as this before. You know, it's the first time something like this happens, and it's very dangerous. You know, and we are just that we get bachelor students that do not program is just a consequence of this dysfunction that, you know, happens early on, and this. But this is one thing, and then we try to, if we are able to build up this knowledge, as I said, but this is then happens in the master, to introduce students to these techniques and try to catch them with showing them that it's not complex at the end of the day, and it's powerful, you know. And it's unmandatory. You know, you can design this way or another way. You can mix. You know, this is also a bit a change in perspective. For a long time, and still we have to fight against this. There is this block thinking. You know, either you are digital or you are not. And with the generation we have now, we are educating now. These categories do not make any sense. You know, these people are digital, but don't even think about being digital. Just, you know, so that you feel free to mix up all the techniques, you know, that you feel free to sketch and program, you know, at the same time, what probably in the 90s was impossible. You know, the people that committed to the digital, you know, were not sketching anything. Maybe they, you know, hidden, yes, but they would not admit, you know, and this thing have lost meaning, you know, for this generation.
I have a question. I have to admit I liked your lecture. Yeah, I found it interesting. But my question is, it's like two questions. One question is, the way you use the drones to create a bridge, do you believe that you can use the same advanced or technique to like improve building construction, like putting nets in higher building constructions? Because when you're looking at like this building right here, it's in a construction and they're like putting out nets. Do you think you can incorporate drones to like put up the nets to improve safety? Also, with the drones, I see that you're trying to put like to incorporate them in building construction by stacking them on top of one another. Have you considered the structure support in the design?
I believe that drones will play a role in the future. It would be strange if they wouldn't, because drones are such simple, wonderfully simple machines that are able to go somewhere in space and do something or deliver something. And if you look at all the logistics of a building site, you know, it's very likely that this possibility will be used soon. But this is not the point of our experiments. These experiments go beyond the question of applicability. You know, they ask or focus on let's say on the potential now with the weaving, you know, of the things, of the process. You know, and there I don't know if this will be, probably this will not be the first application, you know, to exploit this this capability of the machine to fly through something very limited and also maybe changing, you know, in the wind and so on. But for us, it was mandatory to look exactly at this. This was the reason why I showed the drones, you know, assembling sticks, because there we felt not at ease, because we said that this could be done by humans much better. Why are we doing this? You know, so we were looking for something else. But this is not. I mean, I think this will not be the first application. This is very, very complex. First application will. I mean, the first application are already there. Drones are all over the place because there is no simpler way to track something, measure something, monitor. You know. And the next step will be very organic, you know, about delivering things, will be about and here, I mean, you have the perfect environment. It's you know, the drone doesn't care how high up.
Drone cannot fly in New York, especially in Manhattan.
Why?
There are rules for drones to fly. There are
but when this becomes operational, there will be protocols that are tested.
I found very interesting the concept you were talking about, the shifting from the control of form to the control of processes, which has led to a complete freedom of forming in some way, more than form, and goes in some way and crosses fields with art and performances. I mean, while I was looking to those drones, to go back to the drone, images of the performance of Stellar came to my mind, where his body is moved with his mechanical arms from other people. So there is also a concept of displacement between the one who makes, the one who uses, and the tool and the medium that you use for making. It's not the hands of a man that then will use that space, but is a machine, which is a strange kind of concept that is also something that goes with the experiments of art. So I'm wondering, what is your position towards this kind of crossing fields and thresholds and experiments that are philosophically important, because displacement is something that since the 70s the land artists were trying to represent, express in some way, but I think we are arriving to a new way of representing and working through that concept of displacement.
I believe that the boundary between these domains are being renegotiated anyway all the time, and this has a tradition. Now in the specific case of the drone, but of the machines in general, what fascinates us is that, and then we discussed it before with the question of the agency of the machine, the human, that the drone is probably right now the most impressive example. The drone does things autonomously, so has a mission, and this is very critical also. I mean, there is drones like almost everything. First application is war technology, you know. And the big discussion going on now is the drone has an agency to kill, you know, and what does this mean exactly, you know? But now in the playful context of fashion installation means that you have a blueprint, you know how things should be in the end, but the machine, you know, at the level of autonomy that is needed, because you would have no chance to remote control it. It wouldn't make any sense. It would not be about you, you know. You're not automating it in order to have more spare time or reduce costs. It's just you could not, you know, you cannot drive a drone. Or let's say you can drive a drone because there is the control. If you would have 4 levers for the 4 motors, you would go anywhere. And so this decoupling, you know, where the machine looks and searches for the best option, then to finally fly through this, you know, material in order to create the knot and so on. This is very beautiful. But still, it's integrated in a bigger system that is controlled by the designer.
But there is also a level of freedom of unpredictability that you were talking about, that is part of the creation process.
Yeah, and a big part of it relates to the building process itself. So it's in exactly this case, I'm showing you the video of the making, not the final product. Final product is banal, you know. Banal, we could discuss about it, but it's for sure not expressing the beauty of this movement and this autonomy of the machine itself.
Any more questions?
I had one
more question.
Yeah, about the I think you were doing, it was called like ballistic construction with where you're shooting the pieces off, the pieces of clay off. Did you ever think about incorporating like a more aerodynamic design to the projectiles, so that maybe they would land more precisely or something like that, instead of just a cylinder?
Yeah, we did a lot of work, not on aerodynamics, because at this speed this doesn't play such a big role. We're more concerned with, for example, precision in portioning the material. You know, it is very hard because a few grams more or less change a lot. You know, and then we felt that we found out that it was almost impossible in a reasonable process to have full control on the weight of these parts, because then we couldn't have produced so many of them. This was a very, you know, the extrusion and then zack, zack, zack. So we had to work with this unpredictability, and then as soon as we accepted this, we started to look at the other side, at the strategy that would allow us to get as much control as possible over a process that was not under control. And then it got beautiful. It started to make sense. And also the final result is clearly not aiming at full control. This is a bit the difference to the rope bridge. You know, there in remote material deposition, the process is extremely poetic and beautiful, but the final artifact is too. you know, because this process is readable and frozen into the architecture itself.
Yeah, the materiality is informed
Yeah.
by the process.
Yeah.
Last one. Less of a question, more of a comment. And I find this fascinating what you're talking about, relationship of process and design, and the idea of how they operate together, and the conversation about how we might educate an architect in relationship to digital processes. It seems to me that there's this kind of mirroring of the process of design and the design of process, and how those two things work together, and where they mirror off each other. That obviously we need to educate anyone in thinking about design is what is the process of designing something, but then where does that take off to understanding, now I understand what it means to design and what that process is, now how do I design the process of how to make that design?
Yeah, it is big challenges. At the end of the day, it's. But I think the fact that design, the process of design, is also not fully determined, or that this is the fascination on our discipline. You know, we cannot, in other disciplines, students come in and then we have these and these classes, and then we see how their knowledge grows, and then if they're good, they will, if they're not. In architecture, the struggle of the student, and each one of us, if we think back at our first impressions of architecture, at a certain point you're a bit confused and say, what is it all about? You know, what are the rules here? Are there even rules, you know, or not? And to mediate as an educator between this sense of getting lost, you know, and the power of designing something, to create something, we could say from nothing, you know, sometimes, you know, a powerful idea or a process or something like this. And then to see the people being enthusiastic about this experience, you know, this is beautiful. But it's not, I don't think that there is one way, or it's more of a,
Thank you. Please join us upstairs for a reception.
Thank you.